6,2 beta, all right? And we are going to start with example 9. And we're on page 332 of the book. Okay, so here's the question. We want to anti-differentiate this quotient. From 0 to 1, x squared, x squared, take away 4. You got it? And you look at that problem like, well, where do I start? So you say, well, yesterday you told us, in the alpha lesson, you told us that mu would be what's inside the parentheses, which is the general variable. And you say, okay, here, there's no root sign, there's no parentheses. But it makes sense to make mu the denominator. Why? Because if mu is the denominator, then d mu dx is 2x, and d mu is 2x dx. Now this, the top 3 lines in that PDF are all from yesterday. So in order to anti-differentiate this thing, I need 2x dx. What have I got? X dx. So I move this x in the numerator to the right and multiply it by 2. And to balance that, so then this thing represents d mu. And to balance that, I multiply by 1/2 out front. Okay? And this problem is going to be different than what we did yesterday because of this. You now have an option. You can do the problem like we did yesterday. That's in the left-hand column. Or you can do the problem in context of mu, which is in the right-hand column, which is generally more efficient. However, don't go the more efficient way if you don't follow. So I'm looking at this work. You've got 1 over mu. That's the derivative of ln mu. So we do run through the parallel inverse of saying, oh, okay, here's what I got. This whole thing would give me ln the denominator, there's the 1/2. Evaluate between 0 and 1. When you put the values in here, you get 1/2 ln 3/4. That's an exact answer. There's your extra 3 decimal places. But it's really going to be more efficient in the right-hand column. What do you say? Here's what I got, which would give me 1/2 ln mu. But if you do the problem in mu, you have to change the limits. Because the limits are in terms of x. So how do we do that? Well, here's what mu equals. Here's what mu equals, so I put the limits in mu. 0 squared take away 4 is a -4. The lower limit is -4. 1 squared is 1, take away 4 is a -3. And you make the upper limit -3. So you have, ready? 1 over mu du, which is the derivative of ln mu. I put the values in. Now what? You can't take the natural log of a negative number. Meaning what? There is no exponent that you can raise e to give you a negative value. So you need absolute values here. And you see that you get to the same answer. What is that telling you? That the area under the curve from 0 to 1 is negative. This means it's below the x-axis, the net area is negative. So if I want to draw that, I have x divided by x squared plus a -4. And here's the picture. And here's what you're looking for. The area between 0 and 1, which you can see is below the axis. But the reason we're doing example 9 is to give you the option of what's in the right-hand column. But if you want to do the problem in view, without changing that, like we did here, then you have to change the limits. But either way, if you do it correctly, it's going to take you the same answer. So we're going to pause the video, and you're going to use that as your model. You're going to go to problem 63. Okay, 63. Let us do the problem here. Mu is the denominator, yes? So d mu dt equals 1, so d mu equals dt. There's nothing to do, so we can change the limits. So I put 1 in here. 1 plus a negative 3 is negative 2. The upper limit's 2. 2 plus a negative 3 is negative 1. So you get ln mu from there. When you put the absolute value symbols in there, you would get ln 1 subtract ln 2, okay, which is ln 1/2 ln 1/2, which is about negative 693 thousandths. Okay? Now, you need to be aware of this. If we go way back, think about this. If we go back to chapter 3, the derivative, this was the general case for derivatives of exponentials. The derivative of a to the mu is itself times ln a times the derivative of the exponent. Okay. I think I can, if I don't remember that, I think I can pick it up pretty quick if I need it. So that means this. If you're asked to anti-differentiate a to the mu d mu, you need the ln a. ln a is a constant. So you can introduce that. You would have to multiply ln a times d mu. In order to balance that, you have to multiply the reciprocal out front. So this would take you to 1 over ln a times itself plus the constant. Where is the ln a coming from? It's coming from here. So you need to spend some time looking at this table and make sure that's clear to you when you are anti-differentiating exponentials. And then big picture, I try to do this table and kind of summarize what we're doing for power functions. Okay? If I say my power is 2, I have x over 2, I differentiate that, you get x. Differentiate that, you get 1. The derivative of that's a 0. So how do you go to the negatives? If I go negatives working up, I have negative x and a negative 2. That's the derivative of 1 over x. That's x to the negative 1, which will give you negative x to the negative 2. When you move up, you will get from there to there. This is the derivative of ln x. So ln x is the bridge from differentiating to anti-differentiating. Because when you have the power, something raised to the power of 0, that doesn't allow you to go from here to here. You need the ln x there. And then here's a summary. Again, the derivative with respect to x of this is here. The general case is, or I'm sorry, the reciprocal is, the inverse function is, log base A mu. The derivative of that is 1 over mu times ln A in the denominator times d mu. So if you want to anti-differentiate, you need these ln A's, these constants, as part of your d mu. You introduce it. So I just want to go back to something that's less complicated, more of a general case of this. So this PowerPoint is in Canvas. This is ready. This is not to the challenging level of what you just saw. This is more of a C level of understanding, but I think it helps you see what's going on here. You can watch this at your own pace. I started with this question and said, okay, I want to anti-differentiate x cubed dx. That's pretty user-friendly, right? I can rewrite that. You wouldn't do it, but you could. I can rewrite that as x squared times x dx. What happens? This power rule reverse, we do x to the 4th over 4 plus the constant. Yes, because it's indefinite. You need the constant, that's the power rule reverse. But what would the other side give you when you rewrote it? Well, in that case, mu would be x squared. d mu dx would be 2x. Yes, and you would get d mu is 2x dx. So I would put 1/2 front here to multiply x dx by 2. Yes, so you can anti-differentiate. And when you did that, now you would have 1/2 mu d mu. Power rule in reverse. That'd be mu to the 2nd divided by 2 times the 1/2 out front, which is mu to the 2nd over 4. I paste what mu equals, which is x squared, and I would get the same answer. So we took this user-friendly question to the left and forced it into anti-differentiation by substitution to show you how that would work, even though you wouldn't choose to do it. So you get this kind of user-friendly question to come back to it, you get stuck in the substitution. Next thing. This is not on the quiz. However, it's in your book in 6.5. And what's happened is, in the other edition of the book, in the second edition of the book, this was in this section. So the PowerPoint follows the second edition of the book. Subsequently, you can move to 6.5. So it's not part of your material for your forward assessment, but it absolutely is on the AP test, so it doesn't hurt to cover it twice. Okay? So I have to separate the equations. Here's what this means. Suppose you want, this was the derivative. The derivative is 2xy squared, and you want to anti-differentiate that. And this comes up every year. will spend time reviewing for this specifically in the spring. But here's what somebody's going to do that isn't listening. Somebody who's showing up, I don't know, 15 minutes late to class. They would say, oh, this equals 2xy squared. I'm going to anti-differentiate that. Make sense? Yeah, I'm going to anti-differentiate the derivative. Right? Wrong yet. Here's what you have to do. In order to anti-differentiate it, the variable on the right side has to match this variable in the denominator. So for this question, you need to do this. Break it down into two separate questions. Put dx what the x is, and bring the y over to dy. And it becomes two separate problems, which is what separation of variables is. So now what you would get? Power rule reverse. Now this comes up too. This is, why is this not ln y squared? We anti-differentiated this, right? -2 plus 1 to -1, negative y to the negative first, plus some constant, equals power rule reverse x squared plus another constant. It is labeled sum 1 and sum 2. Good? However, here's the other mistake that people make. Oh, I've got this over here. I've got 1 over mu. So I should get ln mu. Why not, Ben?
I'm not sure, but if you were negative y is the power negative 1, it doesn't equal 1. ln y negative 2.
The only reason you get the ln is if the power in the denominator is a 1. Why? Because anti-differentiating that would give you -1 plus 1 is 0 divided by 0. That's what introduces ln. This is just plain old power rule reverse, which would take you here. The opposite of -1 over y equals x squared. Now what? This constant is just combined with it. Like you just add a negative c sub 1 to that. It doesn't, it's just these two are placeholder. This, right? That's 100% correct. Like for today, that's as far as we're going to go. You could do, right? You could say, okay, well, I'm going to take the reciprocal of this side and the reciprocal of that side and multiply both sides by -1. You get y by itself, yes. But this is enough for now to see what this is about. So the issue is going to be, you can anticipate getting separation of variables in math. You need to separate them. Because if you don't, everything you do is spinning your wheels. It's not going to take you anywhere. Right? So that's it for the beta lesson. Yeah, here's a good question. What is the difference between anti-differentiation and an integral? There is no difference. They're synonyms. Okay? And that's important you understand that. But when somebody asks, because they're just two ways of saying the same thing.
What do you consider a variable?
No.
And I see one here in physics, we have was like d, and there was u and x. Would you have to still separate them if there's 3 variables? Or what would happen in that case?
Right, so that's it for